Now I'm going to show you how to model the first example in ABAQUS. So the question states that we have a round bar with a varying diameter, which is subjected to a load of 1000 Newton applied at its top surface, and the bottom bar is completely fixed. So determine the stress and the displacement values in the bar resulting from the load. So if we take a look at this structure, we know that this is a cross-section of an axisymmetry structure. And the question asks us to use the axisymmetry element in ABAQUS to model this problem. And the bar is made of a material with Young's modulus of 200,000, and the Poisson's ratio is 0.3. Now let's take a look at how to model this problem using axisymmetry element in ABAQUS. So first, we need to create a structure. So for axisymmetry, we don't have boundary conditions for it. So when we create an axisymmetry structure, we need to start from sketch. So here you can see we have axisymmetric here. So we need to select this one in order to use the axisymmetry elements in ABAQUS. So here it's still deformable and it's still shell for base features. So here the height is 80. So here I can use 400, use a larger grids. So click continue. So this is 400 by 400. So let's create this cross-section sketch. So we start from 0, 0. So let's put a 0, 0 and hit enter. So we have this point. So you can see this green line represents the axis, because our structure is going to be axisymmetry. So now let's find the coordinate of the second point, this point, which is 40, 0. So let's put 40, 0 and hit enter. So for the second point, it's here. It's 40, 40. Let's put 40, 40 and hit enter. So for the next point, it's here. So this is 20. So the x coordinate of this point is 20, and the height is 40 plus 40 minus 20, so it's 60. So it's 20, 60. Let's put 20, 60 and hit enter. So for next point is this point, which is the x coordinate is 20 and the height is 80. 20, 80. And this point is 0, 80. Let's put 0 and 80 and hit enter. Now we just need to close this sketch. Now we are done with the sketch. So we can hit the middle mouse button and exit sketch and hit done. So you can take a look. We have the cross section of the structure, and this structure is axisymmetry. So this cross section will sweep around this axis to form the entire structure. So for the next few steps, it's exactly similar to what we did before. So we are going to create a material. So this problem is elastic, and we have a Young's modulus of 200,000 and a Poisson ratio of 0.3. 200,000 and 0.3. And let's click OK. And then we create a section. So we use the default solid homogeneous, and we use the default limb section 1. Click continue. And here we are going to use the default one. So the cyclist is 1. So let's click, if you want to change the cyclist, you can click here and put it 2 or any number that you need. So here we just use the default one, which is 1. And then click OK. So now we are going to assign section to this part. Click down, and we only have one section. So we select OK. Next, we are going to measure this part. So you can just give a global size. Let's give 5 and see if it's good enough. This is a little bit coarse. Let's use a smaller mesh size. Let's put 2. And now it looks better. Let's click OK. And then measure this part. Yes. So we can see here we have a quadrilateral element and a triangular elements. And we have some distorted mesh here. So I don't like this. So then in order to minimize the distortion, we can use the mesh control and put it to quad and use this option. And then we can just put OK and delete the old mesh. And then we mesh it again. Now we can see it looks way better than the old mesh. Now let's just assign the mesh element type. So click down. So here you can see from the family, the software uses the default option, which is axisymmetric stress. So we can just leave as it is, and we are going to use for integration. So I can untick reduce integration, and we can see here this is a continuum element, and A represents axisymmetry. So it's a followed bilinear axisymmetry quadrilateral element. This represents followed, and AX represents axisymmetry. And then we click OK. So next we are going to, we have a property, we have the mesh. Next we are going to assemble this. So we create an instance. So we only have one part, and we click OK. So now we have an assembly. Next part we are going to create a step. So we are going to use static analysis. So we use the default limb, which is step 1, and click continue. So this is a linear analysis because the material is linear and the structure is linear. But just in case, so I'll put it I'll turn the nonlinear geometry on. If you have a larger force, it's better to put nonlinear geometry on. Okay. So for incrementation and the solution technique, I'm going to use the default one and click OK. So now we have a step. So next we need to apply boundary conditions and load. So based on this question, so we have a load which is 1000 Newton applied to the top. So here we only have one cross section, so we don't have the top surface. So it's better to convert this to the pressure on the top surface so that we can apply it to this top surface. So the pressure acting applied on the top is equal to the force divided by the area. So remember, this is a axisymmetry structure. So the radius is 20. So it's divided by pi times 20 squared. So let's use this to find the pressure. So it's equal to 1000 and divided by 400 and divided by 3.1415 line, and it's equal to 0.795. So let's put 0.7 so 6. This is our pressure. So let's apply this pressure. So 0.796. So apply load, create a load, and then we call it load 1, and it's pressure. It's in step 1, continue, and we select this edge, and we click down. So let's put a 796, and click OK. So it's pointing downward. So now let's apply boundary conditions. So we are going to fix the bottom surface. So we just use the encastre and click continue, and select this edge and click down, and use encastre, click OK. So now we have everything we need. Now we just need to create a job. So let's call it axisymmetry job. So continue, OK. Now let's submit the job. So we can open monitor. We can use monitor tool to monitor our work. So here you can see the load is this is a linear problem. So the load go from 0 to 1 in one time step, unlike nonlinear problems. So now let's check the result. So we go to results. So we can see the stress. So this is the stress in this cross section. So now I'm going to show you another trick in ABAQUS. So sometimes we simplify the calculation because we know that this structure is an axisymmetry. But when we check the result, we really want to see what it looks like, what the stress looks like in the entire structure. How can we do that? So for this purpose, ABAQUS provided an option called sweep. So we can just replicate this result by sweep this cross section around the axis of symmetry. So let's go to the view and go to the ODB display options. And here we have a sweep and extrude. So for this cross section, so we are going to use the sweep elements. And the angle should be 360. So if you put a 180, so you just have the half cylinder. So if you click apply, you can see here you have half of it. So let's put 360 and click apply. So then you have the entire structure. So if you want to have two more numbers of segments, so you can just increase this and click apply. So it looks smoother. And now, so we have this nice structure with stress, but our computational complexity is way smaller than we model the entire structure. Yeah. So now let's just turn this off. So let's do another thing. So sometimes we want to check if our results is correct or not. So one thing that we can do is to check the reaction force. So we know that we applied a force which is 1000 at the top, right, for this axisymmetry structure. So the reaction, because it's a static problem, so if we applied a 1000 force on the top surface, and based on the equilibrium, we will have a reaction force in the vertical direction should also equal to 1000, right? Let's check this. So one way to check this is we need to create we need to export reaction force at these bottom nodes. So let's go to XY data and we go to create. So we are going to create ODB failed output data. So we click continue. So here I'm going to put a position to unique loadout, and then I can use the reaction force, and I'm going to use the RF2, which represents the vertical reaction force. And if you put a magnitude, it's the total reaction force. So I'm going to use RF2, and here I need to select elements on load. So I'm going to you need to click edit selection first, and then we select these nodes and click this again. And you need to hit the middle mouse button. Now we have selected these 13 nodes. So now I'm going to, if you plot it using the built-in function in ABAQUS, you can see we have 13 linear curves. Each curve represents the reaction force, the vertical reaction force at each node. So we need to sum all reaction forces acting on these nodes so that we can get the total reaction force. So how can we do that? So you can export this data to Excel and do it manually. However, another method is to use the functions in built-in functions in ABAQUS. So now I'm going to show you how to do that. So you need to go to the tools and then XY data create. So this time we go to operate on XY data. So because for the first time we have created XY data using ODB field output. Now we already have this data, so we can go to operate on XY data and click continue. So here you can see we have this data because we already created this data, right? There are 13 points here. So we can use the expression here. So we just add them up. So we double click the first force and use the plus. So you can click here, or you can just click plus on your keyboard and use delete to delete them. Now let's click the second one and use the plus, third one, plus, 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 double click, plus, double click, plus, double click, plus, double click, plus, double click. And then you can plot expression. So then you will have a less curve, which is the sum of all forces applied, the sum of all reaction forces, vertical reaction forces acting on those 13 points. You can see at 0 time step, it's 0. When the load is applied completely, so here we have a force which is 1000, which is exactly what we applied here. So it means the model is correct, right?